We have seen pressure and how it changes in liquids. Now let's use this session to look at how pressure in liquids affects solids that are submerged in them. So to begin everything, let's use this animation as a basis for our analysis. Let's first start by looking at horizontal surfaces and how the liquid above that horizontal surface mounts some form of pressure which is directly proportional to the forces on the surface. So as already stated, pressure applied to the surface of a liquid is directly proportional to the force that is applying that pressure. So in solids, we say that pressure equals force over area. And from a previous session, we have already established that at the horizontal level or at the same height, pressure remains the same in a fluid. So if the pressure is the same at the horizontal level and our solid is also taking a horizontal level in a liquid, then we can say that the pressure applied on the surface is evenly distributed so that an equal force is experienced throughout the surface of the solid. Then by saying so, we can write that the resultant force on the solid is just equal to the pressure at that height times the surface area of that solid. Now, for a solid that is oriented horizontally in a liquid, the resultant force acts directly at the center of that solid. Now let's look at a scenario where we have a vertically submerged surface. Now, unlike the case of horizontally submerged surfaces, we expect that when we go down in a liquid, pressure will increase. Therefore, the force at the top of the solid should be definitely different from the force at the bottom of the solid. So then our formula changes, and then we have the resultant force equals y bar times the specific weight times sine of the angle times the surface area. So alpha in the equation is just the angle between the horizontal surface of the liquid and the solid. Now for a solid that is vertically oriented, it means that the angle that it makes with the liquid surface is 90 degrees. So it changes our formula so that we can have Fr, or the resultant force, equals y bar times the specific weight times the surface area of the solid. So let's come back to our notes. What we've established so far is that in a solid, pressure equals force over area. And from what we've seen so far, we can state the following. That 1. The resultant force always acts perpendicular to the surface of the object. 2. The center of pressure is a point on the object where the resultant force can be found. 3. For a horizontal surface, the center of pressure acts at the center of the object, and the center of pressure for vertical surfaces always acts below the centroid. So let's first look at what y bar is. Y bar is basically the distance from the free surface of the liquid to the centroid of the object. So there are different scenarios where we can look at y bar and then see what y bar will look like. Now for the first example, the centroid of the object is just half of that object, and we said y bar is the distance from the free surface to the centroid of the object. So we can just state that y bar equals 2.5 meters. We have an object that is 4 meters long. Now the centroid of this object will be at the 2-meter height, but y bar is from the free surface to the centroid. So we are going to add the 1 meter to the 2 meters, making up 3 meters for the y bar. For this third example, we need to determine y bar by first determining the slant height of the object. And when we have determined the slant height of the object, we can just divide it into 2, where the centroid is, and then we can say y bar is equal to the distance from the surface to the centroid. We can also do same for example 4 by first determining half of the object, which will be the centroid, and then adding the extra distance that goes to the surface of the liquid. So we should always remember that y bar is the distance from the free surface of the liquid to the centroid of the object. Then we also talked about the center of pressure. So let's explain what center of pressure means. It is a formula that we use to determine exactly where the resultant force acts. For a horizontal surface, we have already stated that the center of pressure acts at the center of the object. But for a vertically submerged surface, the center of pressure acts at a different location. And this is the formula that we use for CP, where we say YCP equals y bar plus I bar over y bar times the area. And I bar is also a formula on its own, which is the second moment of area about the horizontal axis. So for a rectangular surface, I bar equals BH cube over 12, where B is the base and then the H is the height of the rectangular surface. Then for a circular surface, we have I bar equals 1 over 4 pi r to the power 4, where r is the radius of the circle. So these are all formulas that we can use to determine I bar. We have one for semicircle, we have one for triangular surface, and then we have another for an oval surface. So let's look at a simple example. So in this question, we are supposed to determine the hydrostatic force on panels A and B and where they are acting on these panels. Now, if we look at it very well, we see that panel A is rectangular and panel B looks like a circular glass window. So to solve for panel A, we see the resultant force equals y bar times the specific weight times sin alpha times the surface area. Y bar, we have already stated that it is the distance from the free surface to the centroid of the object. Then we can say from the surface to the centroid will be 4 meters. So we finally arrive at a resultant force which is 78,480 newtons or 78.48 kilonewtons. To determine the position at which the resultant force acts, we use the formula for center of pressure, which says that y bar plus I bar over y bar dot area is equal to the center of pressure. This surface is a rectangular surface, so we need to determine the I bar, which is BH cube over 12. So that finally we can say the center of pressure is at 4.083 meters below the surface of the liquid, and it confirms that the center of pressure is always below the centroid of the object, because the centroid was at 4 meters and the center of pressure was 4.083 meters below the surface of the liquid.